Welcome to Lab 4. Um, so, our primary purpose was to simulate and analyze the oscillation of a mass on a spring. Oscillation in this context is driven by the restoring force described by Hooke's law, where the force exerted by the spring is proportional to the displacement from its equilibrium position. We compared real-time tracking data to a computational model to test for accuracy. Using Newton's second law, F equals ma equals negative kx, where k is the spring constant and x is displacement, allowed us to model how position, velocity, and energy evolve over time in an idealized oscillatory system. We used a video analysis tool called Tracker to track the mass's motion frame by frame. First, we calibrated the video to set a scale, which is critical because any miscalibration could induce errors into our measurement. Tracker provided a time series of the mass's position, which we could then differentiate to find velocity and acceleration, even though that's not what we ended up doing. However, this process allowed us to visualize the sinusoidal pattern of position versus time, characteristic of harmonic motion, which helped in validating the periodicity of our motion. The initial values we measured included the mass of the object and the period of oscillation. Using these, we calculated the spring constant k through the relationship T equals 2 pi square root m over k, where T is the period and m is the mass. We also measured the stretch length of the spring to solve for L naught, the natural unstretched length. These values were essential because even small variations in k or L naught can significantly affect the accuracy of the model's predictions, particularly in the amplitude and frequency of oscillations. In our computational model, we applied Newton's second law to resolve the net force at each step, updating the mass's velocity and position iteratively. Using an iterative method allows us to model how the spring force, which depends on displacement, changes as the mass oscillates. We also use the energy principle to calculate the system's kinetic energy and potential energy at each point in time. The potential energy of the spring given by U equals 1/2 k x squared, and the kinetic energy k equals 1/2 mv squared allowed us to check if the total energy remained constant, a key sign of model validity in a closed system. Our results showed the model to be mostly accurate, though we observed a discrepancy in the y position data. This was likely due to a calibration error, which might have shifted the position data slightly. Despite this, the period of oscillation from both x and y position data remained close. This confirmed the periodic nature of harmonic motion and indicated that the calibration discrepancy had only a minor effect on the period itself. Our model's periodic predictions aligned well with the observed data, suggesting that our values for k, m, and L naught were within reasonable accuracy. In our model, we assumed a closed system, meaning we neglected air resistance and frictional forces at the spring attachment. This assumption implies conservation of mechanical energy, where the total energy oscillates between kinetic and potential forms without any loss. While these simplifications allow for more straightforward calculations, they induce slight deviations from reality, as real-world oscillations will gradually lose energy due to dampening forces. What does it mean? Here, the energy principle is satisfied because we see that total energy is constant. This means that energy from other forms, such as potential energy, kinetic energy, and spring energy, all transfer between each other seamlessly without any energy being lost to dampening forces. And we can say this because we assume a closed system. From the data, we estimated the period of oscillation on the x position to be around 1.7 seconds, while the y position data gave us a slightly shorter period of about 1.5 seconds. This slight discrepancy might stem from tracker calibration issues or minor variations in how the mass moves. Nonetheless, the similarity in periods across the two datasets supports the model's predictions. Maybe we could even also say that the differences in periods is just based on how we calculated things, as well, during calculations some values were accessible while some were not. To conclude, this lab successfully modeled the oscillatory motion of a mass on a spring. By analyzing the mass's real-time motion and calculating changes in potential and kinetic energy, we confirmed that our model satisfies both Newton's second law and the energy principle. Overall, the model's predictions closely match with the observed data, underscoring the practical applications of physics principles in modeling oscillatory systems. Thank you for your attention.